You're being recorded, Josh.
It's fine.
No secrets.
Right? I don't think you can go anywhere in the modern day without being recorded.
True.
Sadly. Go ahead.
All right. Well, welcome everyone. It is my pleasure to introduce Josh Lovell here from Harvard CFA. He's going to be talking to us about the development of mature planetary systems. Josh got his PhD in 2022 from the Institute of Astronomy in Cambridge. I think you work with Mark Wyatt, right?
Yep.
And after that, he was the SMA fellow at the CFA, and you're right now a CFA fellow.
That's right.
The difference between went from SMA to CFA fellow, but he's here to talk to us about planetary systems. He's worked on all different types of planetary systems, from young forming systems to mature evolved debris disks. And he obviously likes FOMO hot, so he's a very good person. And take it away.
Thank you, Andreas. Yeah, so I think it was sent around that I was an SMA fellow. I think when maybe when I arranged a trip, I wasn't quite an SMA fellow still. But the difference is that was the submillimeter array that funded me, and now it's just the Center for Astrophysics in general. So thank you for the intro. Yeah, I am going to talk about Fomalhaut today, but I'm going to talk about a whole bunch of other stuff that I've been working on as well. Hopefully, if this shifts forward, perfect. Yes. I want to start by acknowledging a whole bunch of my collaborators here. I've sort of kept the list short, though, just to people with whom I've worked on for some of the key results that I'll present today. As Andreas has said, I've worked on a whole bunch of stuff, and that means so much of this is just left out. So, like, I'm not really going to talk about earlier stage YSOs. I'm not going to talk about protoplanetary disk work that I've done, which is including sort of hunting for new disks, as well as some studies of some giant stuff we found in the universe as well. I should also say that I'm here all week. I'm here until Sunday, but I'll be working until Friday evening. If you want to meet and have a coffee, if you want to meet and chat about something, if you want to go get lunch, there has been a calendar that's sent around, so you can find my details there. You can see when I'm free. I'm trying to keep Thursday blocked off for some collaboration time, but other than that, I'm around to chat. My email's there as well if you just want to write to me. So what I'm going to talk about today then is some context. Since this is an origins seminar, I wanted to try and bring people up to speed with the starting point for my work, which is trying to understand some of the initial configurations of planetary systems, sort of post-protoplanetary disk. And then what we can learn about those types of systems over the next sort of million-year to billion-year timescales. Okay, so the talk's in two halves, basically. There's a whole bunch of stuff that happens very, very early on that I'm really not going to focus on, right? So we have these big, cold, dense molecular clouds, contain everything that goes on to build planets and stars that collapse into these protoplanetary disks. You know, these things that we've seen with ALMA, they look a bit like that. If you look at the really massive ones, they have rings, they have gaps, they have substructures. And basically everything we've learned so far suggests that these have to be the birthplaces for planets, okay? There's too little stuff after this stage in order for us to explain the population of exoplanets that we're pretty much seeing around main sequence stars. And that seems to be true for the planetesimals as well. So we think these are pretty much where all of the bulk planet formation stage is happening. On the other end of the scale, what we know from just looking at the very closest planetary system, our own, the solar system, is that there is some final stage or some late stage architectures, compositions, structures that we can see that allow us to try and infer some evolutionary sequence that goes between these stages. I really love this figure. I first was pointed out by my wife. She bought me actually a post that's about this size that we have up in our flat at the moment. And this shows every body in the solar system that we know of that's, I think, 10 kilometers or larger. And what I think is really striking about this is what your eyes are immediately drawn to. And that's not the planets or the sun, important as these things are, it's the disks. The things that are most evident here are the asteroid belt, and I would say the Kuiper belt, and then this resonant population of bodies nearby to Jupiter. I think this is a really nice thing if you study the debris disks around nearby stars, because it shows the importance and population of these large planetesimals that we're interested in studying. I'll talk a bit more about some of the structures in here in a little bit more detail later. But broadly speaking, the point of my talk is to try and explain what happens in this stage here, a few million years to a few billions of years. How do the solid components of planetary systems evolve during that time? And to what extent do the structures that we see at these late stages appear to be shaped by dynamics? That could be planetary influence dynamics or otherwise. Or to what extent could these be actually inherited from earlier stages? And that's why I study debris disks, okay? Because they allow us to understand the structures of planetary systems through that entire age sequence. A little bit of history, because I think it's fun and I think it's important. That's to say that the whole history of debris disks is basically 40 years old. It started with the first detection of Vega. In fact, I think this was a calibration observation. We pointed IRAS at a star that we were like, well, how can we calibrate to know exactly what the photometry of this source should be? It's just a star, right? And then you see this whopping great excess, okay? This was called the Vega phenomenon back in '84. And we found after pointing this instrument at a number of systems, including Fomalhaut, Beta Pig, Epseri, you'll hear those names a few more times today, that sure enough, actually, this is quite a common thing to occur in the universe. That these are, we learned a little later, not immediately, but we learned a little later that these are actually disks. They're composed of tens of Kelvin-ish dust. And that means that effectively we have these rings around other stars that are like tens to hundreds of AU. They kind of look like the Kuiper belt, right? And we can think of them as exo-Kuiper belts. Sure enough, when we went back to a whole bunch of other stars with Spitzer, with Herschel, we found hundreds, thousands of these things across all main sequence lifetimes. We found disks around white dwarfs. We found disks around main sequence stars too. In fact, we've looked at enough that we know basically 1 in every 3, depending on the spectral type of the source, 1 in every 4 or 5 of these main sequence stars has a debris disk. And we've learned as well by looking at these as a function of their ages, how these things might evolve. We expect that these actually evolve collisionally, much like the disk around our own sun as well. And so the sort of brightness of these objects falls with time. That makes some really old ones hard to see and study, but it doesn't mean that they're not there. I think an important point to say is that these are not simple analogs to protoplanetary disks. Okay, there's a lot of key differences. If we think firstly about what these things are made of, they're dominated by planetesimals and dust. Okay, that's in real contrast to protoplanetary disks where you're dominated by the gaseous component, typically, of 2 orders of magnitude. Gas to dust ratio in a protoplanetary disk, whereas we believe the dust to gas ratios in debris disks are typically, much greater than 1. It's in complete contrast. That means that dynamics in these systems are typically dominated by the solids as well, rather than hydrodynamical effects. The processes that govern the grains we see are typically destructive. Okay, whereas in protoplanetary disks, we believe grains must be growing to build planets and planetesimals. In debris disks, we believe that for the most part, it's grinding down of larger bodies into ever smaller things that can then be dragged inwards or blown outwards. Okay, so these are defined by destructive processes. And indeed, when we look at different sized grains implied by different wavelength observations, sorry, for those online, I'm pointing randomly with a physical stick in real over here, and so you can't see what I'm pointing at, but I'm just waving at Vega at the moment. When we look at the same object at different wavelengths, we are sensitive to different sized grains, different sized dust that is present around these systems. And so on the top left, you see Vega with Hubble in optical, with Webb in the mid-infrared, and then with ALMA at, I think, millimeter, maybe sub-millimeter. It's either 850 microns or 1.3 millimeters. I apologize, I don't know, but it's millimeter-ish. And we see 3 very different structures, right? We see with ALMA a ring with a gap in the center that's been stellar subtracted. But you're typically sensitive to where the dust is in the planetesimal belt itself. The grains that ALMA is sensitive to are not impacted by transport processes. That means when they're formed, after planetesimals have collided, they typically stay in these orbits for a very long time. Certainly long enough that they're living their entire lives at those sorts of radii, and so you don't see any emission being dragged in. That's in contrast to what we're now seeing with James Webb. You see with Vega, the same sort of outer ring, and then a much brighter central region where we believe dust is being dragged inwards, and so you get a much brighter central region. Okay, and so what you would look at with a protoplanetary disk and see here would be something completely different as well. I think I've probably said enough on that slide. So there's some context, and that sort of sets the stage for why I'm interested in looking at younger systems, places where we might think things will be brighter. And when they're brighter, that means we can start to look much further away, and therefore to young star-forming regions where we can actually understand what the birth population of these disks might be. So sure enough, if we believe protoplanetary disks are forming planetesimals, we might also believe that they should be forming planetesimal rings, these debris disks, these very, very early stage debris disks anyway. And so one of the investigations I did in my PhD was to look at class 3 stars. Right? Class 3 stars are effectively, I mean, they've been called diskless stars for a very long time. I think that's a very incorrect name because we know that they have disks. What it really means, though, is they have very low, if any at all, infrared excess. So these are defined purely observationally in terms of the spectral slope from 2 microns, to about 10 or 20 microns. And if that spectral slope is sufficiently steep, then we've called them class 3. And that basically means they lack a warm excess. That doesn't say anything about the cold dust, okay? And that was one of the reasons we looked at them, because sure enough, you might lack emission near to your star, or at least significant emission near to your star, but you may still host a very large population of cold outer dust, like we'd expect with a debris disk. These systems are also defined as having little to no accretion as well, which is another signifier that these are much beyond the evolutionary stage of the protoplanetary disk, where things are still basically being buried onto the star or being ejected from the systems themselves. And so this investigation we ran during my PhD, and we published a few years back, was to look at a significantly sized sample of class 3 stars in the Lupus star-forming region. So this is a very young place, 1 to 3 million years old. And what you see on this plot are all of the detections of the class 2s that you can see in blue and pink or purple, depending on your angle that you're looking at this. And what you see in the class 3 population is the orange dots as well. And most of them are upper limits. Okay? For the most part, when we stared at these things, we didn't see much at all. The class 2s, if we look at the total dust mass, we make some approximate assumptions there for the temperature and opacity properties of the dust that we're looking at. If you make the same approximations for the class 3 systems, you see that there's a huge gap in where you're detecting class 2s and where you're seeing class 3s. That means that there must be some significant amount of evolution that's happening between the class 2 and 3 stage. Importantly, though, we did see some systems. It's not that we saw nothing at all. We saw a number of compact rings, compact disks, I should say, that had size scales of approximately 50, 60 AU and smaller. And we saw one system, which you'll have to take my word for it, you can model as a ring. That's sort of a disk about 90 AU, which sounds a lot like the debris disks that we're seeing around most of the main sequence stars. These are, typically 50 to 200 AU or so. And we also saw a couple of hot disks, things that did have IR excesses, but they were still below that spectral slope cutoff. So class 3s with potentially, either remnant emission from a primordial disk or potentially massive asteroid belt type analogs. And a question after this was, oh gosh, that's gone. I've fallen out of Zoom. Hold on. I'm still reconnecting. Well, that's no good. I've got connection issues.
You want to try the.
Hold on. It's definitely my laptop. Hold on.
Just Wi-Fi.
I couldn't get an edge around this morning.
You can try that.
Right.
You did it on the laptop.
Okay.
Okay, he's back.
I'm going through my phone's Wi-Fi.
I just guessed access.
Share. Okay. Right, I'll be back. Am I screen sharing? Can everyone hear me again?
Yeah, I think so.
Okay, right. Apologies for that. I think I got to the end of this slide. Basically, what I wanted to do was understand if this was typical. One of the reasons that I wanted to do that was this was a sample of 30 systems. We know that in star-forming regions, there are literally hundreds, sometimes thousands of class 3s, even in comparison to class 2s. They are often the dominant population of young stars in star-forming regions. And yet we're absolutely biased to class 2 detections. We haven't even touched the tip of the iceberg yet with class 3s. So I sort of set this as a bit of a mission over my postdoc to try and look at some of these star-forming regions in a more complete sense. And there's a real lag now. Oh no. Why is this happening? I can see that on here it's changed.
Yeah, it's just a little bit lag.
Yeah. See, I'm gonna carry on. Sure, okay. We'll carry on and cry for now. It might have just been the first slide, but when I did that earlier, it was a little slow in the first transition. Anyway, what I've tried to do during my postdoc is really expand the survey space for these class 3s to get a much better understanding of the typical properties of these objects. I'm going to focus the next couple of slides on the torus survey that I've run, where we've looked at basically 66, I think, total systems. I'm writing this paper up now. But I've also observed 100 systems in Cepheus, and then all of the A stars in SCOSEN, all 250 sources there with ALMA as well. I think prior to this work, the sort of state of the art was a paper by Anna Michel, where they presented 85mm observations. That's basically everything ALMA had looked at as of 2021. And now I think I've brought the statistics up to over 500 or so in terms of their SMA and ALMA observations. We can start to say something much more broad about the spectral type dependencies and the typical properties. And here is a figure in prep, but it's not going to change basically in the paper that I'm writing. So again, we're seeing effectively the same thing that we saw in lupus. But what I've done here is made sure that the population is now complete. So in lupus, there were some stars basically missing from the sample space that we covered. So although we had a reasonably large sample, we hadn't looked at everything. Whereas above about 0.8 solar masses in torus now, we've looked at all of the class 3s. And guess what? We see nothing. Now, this was the SMA. This gives us mass limits of sort of 0.2, I think, to about 0.8 Earth masses. And every protoplanetary disk in that same stellar mass range is detected. And so that's telling us that there truly is a connection between what's happening in the millimeter and the infrared. Otherwise, the YSO classifications, this class 2 and class 3, which has no bearing on what we see in the millimeter observations. And so, although we're not actually detecting any belts, this non-detection sample that we're seeing is consistent still with what we'd expect as if these were all debris disks. Okay. So what we've been able to conclude is that this population at millimeter wavelengths is really faint. You know, we're looking at 0.1 to 1 Earth masses of dust at most. And that mass distribution is therefore completely consistent with what we expect on the main sequence. If you take a step further and say, well, we've looked at everything in torus. Torus is like 1 to 3 million years. Now, if you make the assumption that these stars are all born on approximately the same timescale within, the last 1 to 3 million years, you can start to put an estimate on how much sort of dust mass is being converted from the class 2 stage to the class 3 into either planetesimals or is being dispersed out of the system. And effectively, you can take the top end, so you can take the class 2 distribution and find means and medians and statistics to describe how much dust mass those have. And then if you make the comparison to the class 3 stage, you can say that, tens of Earth masses on million-year timescales must be being dispersed. Okay, I believe that's in that, and that's just in the dust. I believe if you scale that up by a factor of 10 to 100 as you would expect for the gas, that then gives you a number which is basically comparable with wind-driven disk models as well and proto-evaporative wind-driven models. What I'm interested in, though, is how much could be converted into planetesimals. And that remains an open question until we actually start to resolve the belts themselves. So what I'm trying to do is get deeper observations of these systems so that we can start to see where their disks actually lie. It's also unclear, based on these data so far, what dispersal mechanism is actually favored. Since we basically only still have broad-scale non-detections. I should say what I'm showing here is the torus data, but the same picture is seen in SCO-SEN, the same picture is seen in Cepheus. We're basically not seeing anything, and when we do, it's all way down here in contrast to the class 2s. So it really does appear like there is a major millimeter property difference between these two evolutionary stages.
Sorry, Josh.
Yep.
I'd like to, this is a very important point I wanted to clarify. So you said at the beginning that 1 out of 3 stars, they show a debris belt.
Yeah.
Right? And now you tell me there are 258 type stars and you don't detect any debris. So is the sensitivity to the SCO-SEN comparable to the sensitivity that you have to the nearby objects?
No.
No.
Okay. So SCO-SEN is like 150 parsecs.
You cannot have that sensitivity.
No. The mass sensitivity in SCO-SEN is of the order Earth mass level.
So that explains it.
Yes. Yeah, I mean, even the upper end masses of debris disks are about 0.1 Earth masses in dust. Most of them sit below that, down to like 100th, even 1,000th of an Earth mass. And so, although you can make a strong distinction between the sort of class 2 protoplanetary disk level masses, we're still in this regime where only the very most massive disks would even be detectable at star-forming region distances.
There's also
Question.
Yeah, there's also a question.
Please, yeah.
So you can read it there. I can read it now. So what is the fraction of the infrared luminosity distribution of your class 3 disks?
Anything from 10 to the minus 2 downwards, Carl. That will be in the paper. I can't off the top of my head remember, but they are in the sort of classical observational limit that we've used to describe debris disks, which is like 0.01 and less. Does that help?
Thank you.
Cool.
Since we're asking a question.
Yeah, please.
Did you investigate the environmental effects, like distances from higher mass stars in the regions and disk fractions?
No.
Okay.
No, in Taurus is like a relatively low mass star-forming region. There are some B stars in there, and some B stars are in our sample, but these are like B9s. I don't believe there are any O stars at all. I don't think there's anything much earlier than B9. Those might have had some impact on their nearby environments, but it's not like we're looking at an Orion type star-forming region. SCO-SEN does have a lot more B stars. I just haven't dug into this data yet to see if there's any environmental impacts yet. So, but that's something that can be done with the data given the volume that we have here. Sure.
Piggybacking on this, still talking about the environment, you mentioned some of the disks were more compact. So I was wondering about binarity. Like if you have like stellar companions, could that explain some of those?
For sure.
Yeah.
For sure. I mean, I've got to think back to what we did in 2021. We did have an analysis of which systems were and were not binaries. I think it was not statistically conclusive that was having a major impact, but I think we're in the sort of regime of small number statistics there. And so, I mean, we know that binaries do impact the properties of disks, certainly their radial distributions, depending on relative separations. And I think given the unknown binary population in some of these Starfman regions, it's very plausible that's an operation and we wouldn't yet even know about it. Okay, cool. I think I'm going to be very brief on this slide since we've been doing questions, and I want to get to the sort of later stage stuff. And that's to say that we do actually see gas in some of these systems as well. They're even more rarely than dust, but there's gas there. And sometimes it also shows peculiar line properties, such as really broad widths, whilst being spatially resolved. So maybe we're actually seeing some very late stage evaporative processes or wind processes that are happening in the class 3s, or this is telling us something even more interesting about the typical environments of very, very young debris disks. This is getting you ALMA time this year, so keep your eyes peeled in the next year or two as to what might be happening around this system in particular. In the interest of time, though, I want to jump forward and just end on this for the early stage stuff. And that's something that I don't think I'd appreciated before I'd started running these surveys, that if anybody plans to follow up on them, should definitely account for, and I'm certainly trying to do my best to do that now. And that is a fundamental property of these class 3s, is they're very young. We know that young stars are also very active. And sometimes what you think and infer initially as a disk is not a disk at all. It's actually a star going through some very bright flaring type process. So the two figures that I've shown here are all of the data for one night of the SMA with looking at the system HD 283572, which is a Myr Gyr type, not classically what you'd think of as an active type star. And then if you stack the other 7 nights of data that we had on this system, you see there's nothing there. And the sensitivity of that 7 nights is of the order √7 deeper than that 1 night. And so the fact that we see nothing over there and something over 1 night means that it was doing something very active during a very short period. So I published this work a couple of years back. But I think really the point that I want to make here is not that these flares are interesting in their own right, which they are. It's that when we're running these surveys of YSOs at this stage, we need to be very careful that we're not folding in variable stellar events into our properties of disks. It would have been very, very easy for me to have just collapsed all that data and said, there's like a Miller-Jansky source in there, that's a disk of about an Earth mass. But because we had a wide time baseline at which we observed this source, we were able to conclude, in fact, no, that's not true. This is some millimeter radio type processes that were actually sensitive to 1.3 millimeters. And so, yes, I think that's an important methodological point that I've concluded in running this type of work.
I have a question.
Please.
So how could we really distinguish the two different processes? Should we just have the spatially resolve the data to confirm it's a disk, or we can use the multi-wavelength to really see the differences?
Multi-wavelength, yes. Resolution, yes. What we managed to do here was look at the spectral slope in the data as well. And so these very energetic radio events that I think we were seeing, these non-thermal sort of synchrotron, gyrosynchrotron type emission mechanisms have really sharp rising spectral slope with frequency, with wavelength, sorry. And so what you typically expect from a dust spectrum is a slope that falls with wavelength. This is actually doing the complete opposite. So there's one way that you can infer this without even needing to resolve or go to, but without needing to resolve. That required multi-wavelength emission though.
Okay.
We were just fortunate with the SMA that our bandwidth's like 48 gigahertz. And so we could actually use the 2 sidebands and get a reasonable enough constraint to be like, well, this isn't dust. The other thing you can resort to is physics. If this was emission coming from a collisional belt, it would be there every time you looked back at it. And so the fact that this was so variable at millimeter wavelengths was really telling us something about this not being from sort of a collisional grinding process that's happening at tens of AU. Otherwise, we'd have seen something that was much more stable. Okay. Resolving the disk would have also, or not resolving it, could have helped. But that also leads to some other ambiguity. So I think the the multi-frequency angle is probably a more convincing route to go. But, you know, if you'd have resolved a disk there, that would have been a very weird thing to have seen on the radio for a non-thermal process. No worries. So here are some like broad conclusions that I've drawn from all of this work. Oh gosh, it's a little lag, isn't there? I'm sorry about this. And that is that I think these class 3 YSOs, despite them having been not typically well studied, are actually very, very important for constraining what is going on immediately after a protoplanetary disk is dispersed and at the immediate start of a main sequence star and debris disk's lifetime, even if they're hard to see. A lot of this is coming down to sensitivity issues that I think we can beat with upgraded technologies that I can talk about a bit later. I say they appear as common as those around field stars. The mass distributions that we're seeing around class 3s for those with disks appear in complete consistency with that we would expect for debris disks. So I think there is an underlying population of young planetesimal belts at these ages. Certainly, for sure, we need better resolution to start inferring any other properties of these systems, their radii, for example, to try and understand how that might relate to the observed population. So a point on this is, more recently, there was a study published by Luca Matra, the Reason Survey, and they show an evolution in the radial distribution with age for debris disks. And that's what you would expect from collisional evolutionary processes. The inner regions of disks grind down faster than the outer regions. And so when you look at sort of 10 to 30 million year population, you compare that to hundreds of million year population, you see a bias in the average radius. Until we're actually resolving disks down at this age, it's very hard to put it into that framework, but that would be an important test to do in the next, epoch of observations. I want to move now on to sort of higher resolution studies of debris disks. What we can learn from studying substructures about how planetary systems evolve over tens to hundreds to thousands of millions of years. So we're moving on beyond the class 3 stage now to try and investigate and understand the development over longer term timescales. A lot of the context for this now, in my view, has been set by the last 10 years, 15 years almost of ALMA. And that's looking at nearby debris disks, places where we can get down to few AU resolution. Okay, so we have here systems like Epseri, that's like 3 parsecs away. That's the closest debris disk that we know of, at least, that has a very well resolved outer disk. Through to systems like 9945, 107146, these are at like 18 to 25 parsecs, I think. Q&A is at like 17 parsecs. So these systems are really nearby. Now, even though they're faint, they're low mass, actually, when they're that much closer to us, we can start to see in tremendous detail the morphologies of these disks and indeed the presence of substructures. So we can see that ALMA has shown that there are, rings, gaps, double rings, clumpy features, arc-like features in these systems. ALMA has shown us that these have substructures themselves. Another important context for all of this is that when it loads, we know nearby debris disks and nearby stars, many of these have planets. So here is a very famous example of a system that has both an outer cold debris disk and an inner planetary system, which, with better internet and Wi-Fi coverage, you would show nice Keplerian orbits. You can kind of see it by eye, I guess, a bit. And so one of the connections I think many of us in the community are trying to make is between this planetary system architecture and the debris disk architectures beyond them. And there's very good reason to believe that planets and disks fundamentally are related. Okay. What I'm showing on the left is the distribution of asteroids as a function of semi-major axis in the solar system. And you see all of these peaks and troughs, okay? And if you correlate those to mean motion resonances with Jupiter, you see wherever you have a mean motion resonance, a strong one, you have a complete depletion in the asteroid population, okay? That's a historical dynamical shaping from this massive planet. You could argue if you'd never seen Jupiter, but you had seen the asteroids, you could infer the presence of a, Jupiter massish body at like 5.2 AU based on the resonance structure in the disk. Okay. If we therefore extrapolate that to exoplanetary systems, and we have good enough information about the structural morphologies of the disk, we can make the same argument. We haven't seen the planets, but we've seen sufficiently highly resolved substructures and structures. Can that give us some information on unseen planetary systems? And this is one of the topics that I'm interested in. That's trying to infer from these very high resolution maps potential exoplanetary components and architectures. I'm going to talk a bit about eccentricity. I think the image of Fomalhaut probably gave that away, that this is a particular substructure that I'm interested in and have worked on. And start by motivating this really from first principles. And that is, imagine the simplest scenario you possibly could. A three-body system, a star, an eccentric planet, and a planetesimal. And there are basically two ways that you can set that system up. You can have a star in the center, and then an eccentric planet sat outside it, and then a planetesimal beyond that orbit. Or you could flip the planet and the planetesimal around. Those are two fine configurations for this architecture. If you like maths, you can buy this book, and you can show, if you follow the sort of disturbing function maths, which is a bit hairy. Antonin probably disagrees, but it can get messy if you go beyond first order terms. That if you have a planet inside the orbit of a sub-dominant mass body, that the eccentricity of that outer body is related to that of the planet and the planet's position relative to its orbit. Okay. Likewise, if you have a planet on the outside of that planetesimal, it can have a sort of flipped relation. What you see here is a relationship where if you have a planet inside a planetesimal's orbit, that planetesimal has a semi-major axis which will fall with its distance from the planet. And that's opposite if the planetesimal's inside that of the planet. Let's extend that now, because we don't just have a simple system of three bodies, do we? We have a star, a planet, and a planetesimal disk. If those are then extrapolated into a much larger distribution of bodies that then follow the full azimuth of a disk, you could argue, based on this type of analysis, that if that planet dominates the mass of that belt, it will also invoke these types of eccentricity profiles into a disk. So this is a proposition me and a colleague of mine, Elliot Lynch, put forward a few years ago, and basically, from just a purely theoretical standpoint, tried to simulate what we would expect to see. And if you have a few configurations of just simple rings around systems that are defined by these different eccentricity profiles, you get quite different mass distributions that you see here. These are just lines. There's no physics involved in the lines themselves. But the thing I think is worth pointing out is the way that orbits get bunched up is strongly dependent on the type of eccentricity profiles that you have. Okay. I started thinking about this in a little bit more detail and tried to see where this might have actually arisen in nature. I extended some of the code that me and Elliot had written and published a little while ago. And what you see here are the properties of a Fomalhaut-like system, but with different eccentricity profiles, to sort of demonstrate that this isn't just a mathematical trick, but it's actually a very noticeable impact that these profiles have on the mass distributions of planetesimal disks. What you see on the left-hand side is an eccentricity profile that's flat if it's constant. If you didn't care about the eccentricity and you gave every particle in that disk the same value through the disk, that's the typical surface density distribution that you would see. If instead, however, you gave this thing a falling profile, something more akin to putting a planet inside the ring, you get something that's on the right-hand side. You end up bunching up orbits effectively more tightly at apocenter and spacing them out at pericenter. So it ultimately leads to surface density distributions that are, to first order, very different. Very noticeably different if you look at the lower panel when we look at these in X and Y rather than R and phi. So what this eccentricity gradient typically does is reshape the widths of the disk relative to where the pericenter argument is for the system. And where the pericenter argument is literally just the direction at which the pericenter, i.e. the closest approach of an eccentric orbit is to the star. Why did I do this for Fomalhaut? Because we had excellent data for it. Data that I didn't realize existed until a few years ago. And when I started the CFA, I was talking about this idea, this conceptual idea with David Wilner, and he was like, hey, if you looked at the new ALMA data yet? I was like, no. He was like, you should, because it sounds like what you're describing. It sounds like a system where we do have a much broader disk at pericenter and a much narrower one at apicenter where we see this brightness enhancement. And sure enough, well, I'll come back to that. I should say we actually see the opposite with Myr Gyr. There's a lot of people here who use web. This is the beautiful data that Andras published some years back, a few years back. And you actually see some of the opposite types of structure in this disk. You can ask me about that if you're interested. But whereas in ALMA, you're seeing a much brighter system at the top, with JWST Myr Gyr, you're seeing a much brighter region in pericenter. That's important for reasons that I can come back to. I'm going to be brief here just to say that we ran 2 investigations in parallel for Fomalhaut to see if we could fully exclude the possibility that this isn't just some complex eccentricity distribution at play, and it is actually something with a falling profile. And what you see here are some of the simulations that Jay Chatidi ran. Jay is a graduate student working with Meredith McGregor at Johns Hopkins. And Jay basically excluded the possibility that you can describe this system with the models that had been published some years back by Grant Kennedy. For the newest data, it just can't work. There's no combination of free eccentricity that allows you to fit the ring's width and brightness asymmetries. In contrast, I was able to show if instead we neglect the possibility that this is a fixed eccentricity profile, but it's something that's falling, you can describe this ring really nicely. I would say it's imperfect, but to first order, you are fully describing the width of the disk at both the pericenter and apicenter, as well as the brightness enhancement. And doing both of those things simultaneously is where previous models had not been successful. And this is about as simple as it gets. This assumes like a Gaussian radial distribution, and there's just 6 free parameters to fit this. You just need to know an effective width, a radius, an eccentricity, pericenter argument, and the gradient, the eccentricity gradient, and you can basically describe the system pretty much full on. Yeah.
Can I have a quick question?
Yeah, please.
So some of this is obviously projection effect as well. So that true pericenter is not there of the orbit for the system. It's offset by like, I don't know, 15.
Yeah, it's like down here. It's basically due south from the star. That's right.
So that's taken into account.
Oh, yeah, for sure. Yeah. I say use 6 free parameters. I mean, you need to know the position angle and the inclination as well. But yeah, we've accounted for the potential of that pericenter angle is not along the major axis of the disk, for sure. Please.
So is there a planet in the system?
None known. None known.
I know, but
yeah.
Is that what you're saying?
Well, what I can I try this, or is it related?
Yeah, it was related, actually. I just wanted to really understand when you say you have a variation in eccentricity and Jay couldn't figure out, is this the planet that needs to have its eccentricity varying as it imposes?
I'm not modeling a planet.
Okay.
I'm just modeling the eccentricity architecture of the ring.
Excellent.
Yes.
We'll have to talk.
Yes, please. But coming back to that, you can make some first order estimates of what this tells you about a planet, right? And that's what we did in the study as well. We did make use of the Myr Gyr data by saying, well, there are regions of this disk in this system where if you stick a planet, you're going to break the structure that you see with Myr. And there are two sort of unique-ish solutions, and one is inside the intermediate belt that you see with Webb, and then there's one that's between the intermediate belt and the outer belt. And if you have planets in those locations, we showed for some n-body simulations that you do back out the same typical structure that we're seeing in the ALMA disk as well. And so what you find is you need like an eccentric exo Neptune or some coldish eccentric super Earth, given the masses of the bodies and what that also implies for where resonant locations would be. You can, broadly speaking, infer the properties of what an eccentric planet could be consistently with the ALMA data and the Myr data. So yes, a big question that I'm still grappling with is whether or not this is a unique planet signature or not. So I made the argument earlier that you stick a planet inside a planetesimal's orbit and you do expect this relationship with semi-major axis. And yet we've seen this apocenter glow type structure in some protoplanetary disks as well. And it doesn't leave beyond doubt the possibility that this is still an inherited structure. This is one question that I have for people here, either, well, probably after this talk, otherwise I'll never get to the end of it. What they think the unique solutions are for a planetesimal disk that's interacted with a planet. Where can we say for sure there is a smoking gun signature? I'd really like this to be one, but I think the possibility that this is not an inherited feature has not been ruled out yet, I would say. I make more of a discussion on that in the paper based on what we see in terms of the time evolution of the eccentric architectures of the ring. I like the idea that there's a planet there. Doesn't necessarily mean there is one. I'll be brief here and say that there's a whole bunch of other systems, right? Eccentricity is a fundamental parameter of any orbit. It should therefore be a fundamental parameter of any conglomeration of orbits of planetesimals. Now, eccentricity at the moment seems like a rare thing to see in a debris disk. We have circa 5 or 6 examples, I would say, with ALMA. 3 of which I think are visible by eye. The other 2 that are worth noting are 202628 and 53143. You can see that there is an offset star from the very centers of these rings. I've been working on some ARCS data that I'll talk about shortly for 4796, for 15115 and 32297, which also show evidence of eccentricity as well from the high resolution ALMA data that we have. And I've been lucky enough to have a JWST program to look at 15115 and 53143 with Myr as well. Which is one reason that I'm here, because I'm not a Myr expert, but Andres is, and Andres is on the program. So we're going to try and figure out what we can is present in the 53143 data this week. I want to highlight briefly some work which is ongoing that we're hoping to conclude soon that I've been going through with Otto Ulrich, who is an undergraduate at Trinity College Dublin that I've been working with. He came to work at the CFA for like 10 weeks. And we wanted to try and do the opposite, right? We wanted to look at a very circular system and see what limits we could say there are on the eccentricity of the ring of Epseri. So we basically took the same code architecture that I developed for Fomalhaut and said, what about this other disk? What can we say about the eccentricity there? I mean, as it stands, the lowest eccentricity inferred that is measured with ALMA is like 8 or 9%, I think 9 or 10% actually. We wanted to see if there's any evidence of even a low level here. Given that this is so close, like we're looking at 3 parsecs here and we have such good data, if we could see even like some sort of 2% levels of it here, we figured we should try. And what Otto was able to do is show that it's got to be really small. You know, you can't have an eccentric ring of more than 3% here to be consistent with the ALMA data, given all of the higher order effects that we discussed earlier. Okay. That seems to be, again, nicely agreeing with the limits that Skylar published like only a couple of months ago from Myr as well. So those data that JWST looked at were modeled, and they found as well that this has to be consistent with some circular planetary system or near circular. which it turns out also agrees with the sort of structure of the planet's orbits as well. So yeah, Otto's work is in work, but we are pulling a paper together as we speak and hoping that we can publish that by the summer, but let's see how that goes.
Okay, so question.
Of course.
What is the expected eccentricity of the solar system belt, like the Kuiper belt?
What is the expected?
Or measured. I think it's also like very circular.
Well, it's complicated. It depends what you look at. So we have like excited populations of bodies which are on very highly eccentric orbits. I think the problem is for a disk that's so far away, you can infer like a bulk, a mean. Whereas the solar system, we have such good data, we are typically looking at the orbits of individual objects, and those can vary a lot. I'm not sure what the statistical bulk is in the solar system, but for the excited dynamical population, you know, some of these bodies are at like 0.2, 0.3, 0.4, even higher. And then there are some bodies that are, you know, cold, unexcited, very low eccentricity. So it basically varies where you look in the belt. I should say something about arcs. I'm going to talk more on arcs on Friday. I'm giving one of the flash seminars at NOAA Lab. But I thought it would be important to at least highlight a whole bunch of the cool results that are being published next week. In fact, a week today. All of the ARCS papers will be on the archive on Tuesday, as well as a nice press release. What is ARCS? ARCS is the first ALMA program that was dedicated to studying debris disks. We looked at 18 new systems, so 18 systems. We got new data on 18 systems, and we had 6 systems as well that archival data was good enough that they met our sample definitions. And so we have a really nice gallery of 24 extremely well-resolved, highly sensitive data on nearby debris disk-bearing objects. And I think the fundamental question that ARCS was trying to solve, there were several, but for me, this was the big one. And that is, from D-Sharp, from surveys of protoplanetary disks, we're seeing these beautiful substructured rings. When we looked at debris disks up until, you know, a few years ago, what we saw were kind of blurry, extended distributions of dust. And there was a question, and that is, are they truly wide belts, or are these just like multiple rings that are being smoothed given the resolution of the data? And that, I think, is important and fundamental to investigating, you know, whether or not there are planets in gaps or what the ultimate substructures are within these systems. And here is the gallery of all of the ARCS data that we now have, which I think is really, really stunning. And there's a lot of detail in here. And I will, as I say, talk more in detail about some of the results on Friday. But I think one of the fundamental things that we're seeing are many of these systems truly are wide distributions of planetesimals. They don't really fit the picture of what we're seeing from the higher resolution protoplanetary disks. It doesn't look like, if you plotted their distributions, these are a population of systems that can't be, let me rephrase this. It looks like if you compare the two distributions, there has to be something dynamically going on in order to go from these narrow protoplanetary rings to these broad debris rings. When we're looking at the vertical profile of some of these systems, the ones that are really highly inclined, we've seen that these are extremely flat in almost all cases, like really, really flat. These are like, I want to call them pancakes, but they're kind of too narrow as well at times. They are really, really narrow. And that's telling us something fundamental about the masses of these disks, given the stirring that would be present if there were sort of larger bodies inside these belts. We're also seeing some things that kind of do look like protoplanetary disks in terms of their properties, and that is when we're looking at the gas of these systems. There are 6 objects in here that have CO, and they have a lot of CO. They have CO at levels typical of a protoplanetary object, a protoplanetary disk object. And they also have 12 CO, 13 CO isotopolog ratios that look exactly like you would expect from protoplanetary disks. Now, that could just be an optical depth effect, or it could be telling us something more fundamental about the abundance of CO and other molecules are present in these earlier systems. All of those gas-rich ones, CO-rich ones, are typically young objects. Something that I've done is investigate the asymmetries. As I've said, I'll focus more on this on the Flash Talk on Friday. But like 10 out of 24 of these targets do have some asymmetric structure of some sort. We have this brightness enhancement in the southern answer of Q1 we have this arc-like feature in 92945. Beta Pic has a sort of radial emission enhancement towards the north. Others have other properties, but one very unique feature that we saw was in 49 Ceti. This is one of the CO-rich ones that appears to have a twist or warp-like structure as well. This is not the best figure for it. You'll see a much better figure for this either on Friday or next week in the papers. But the peak offsets along the major axis on those answer are not along the bulk of that of the disk. And it turns out if you compare that to the CO distribution that Meredith Hughes published 7 years ago, these match up as well. So it looks like there's some peculiar hydrodynamical warping effect that's present in this object. 49 Ceti, I think it's like 40, 50 million years old as well. So there's a whole bunch of new discoveries that ARCS has made, things that we weren't expecting, as well as answering questions that we attempted to probe. I am going to focus the next few years of my work on some of the nicest asymmetric systems here to try and get a better understanding of these fundamental properties such as eccentricity. So I guess conclusion 2, and I don't know what the time is because that's wrong.
Yeah, you still have like a few minutes.
I got a few minutes, right? So I should probably wrap up here to sort of say that we are now getting down to AU scale resolution. It's really the case for some of these ARCS data. They're stunning. And that alongside JWST are showing us very strong evidence of these long-term secular dynamical type interactions that we might expect to see. Asymmetries are appearing to be the norm rather than some peculiar subset of systems that have them. I would say we are lacking theorist support here. It's not to say we don't have theorists, but I think that this is an area of real value as an observer, and that is more theorists' time to tell us what unique signatures are of planet disk interactions. There's lots of things that look like, you know, to first order, you plug a planet in a system, you get these gaps and rings. Fine, that's not a unique signature. What I'm really interested in trying to understand from people who can model this is what are the things we should hunt for, where we can actually infer where exoplanets might actually harbor and habiting out in exoplanetary systems. I think we have certainly only just scratched the surface with JWST, and ALMA has ALMA 2030 upgrades that are coming online in the next few years. There's an ALMA 2040 project, science scoping, that is trying to extend ALMA's sensitivity and resolution by an order of magnitude. And you can only imagine then what would be possible if we had that ARC sample with 10 times resolution and sensitivity. It would be really exquisite. There are a couple of other instruments that I think are probably worth mentioning, although there's no time to really discuss. One of them is PRIMA. I want to highlight that because the far infrared is completely absent in all of this. And yet any circumstellar disk at tens to hundreds of AU, that is where its emission is brightest. If we're going to understand anything about the bulk properties of these objects, we're going to need a new far infrared probe. That's a fairly fundamental point. And there are other possibilities as well in the submillimeter with this 50-meter Atlas concept from the ground in Atacama. There are other things I'm excited about, but we could chat about those over coffee at some point this week if you're interested. I'm going to stop there. I think I've concluded 2 times already, so I'm happy to take questions. I know we've discussed stuff, but I'm around all week, so thank you.
So there's a comment from Renu online. She said, based on the giant planet's eccentricities, we would expect the solar system's Kuiper belt objects to have very low forced eccentricity, which is much less than 0.05.
Okay.
That follows our discussions. Do we have any other questions?
Based on the giant planets?
Yeah.
Yeah, okay.
We still probably have time for one or two quick questions. Okay, I think we already had the in-depth discussion throughout our presentation. So Josh will stay with us for the following week, and there is a sample sheet, and you can check out that if you want to have more discussions with him. And he will also give another flash talk on Friday lunch at NORLAB, and feel free to go around there. And thanks for coming today, and thank you, Josh.
Thank you.